All right, thanks, Sharon. And I'd also like to go ahead and thank State of Utah for funding this project, as well as Marathon for co-funding. And want to point out our thanks to UDAC staff for their technical contributions as well. And for Dr. Randy Martin for providing some data from a recent field campaign, and also for thanks to some of our colleagues for helping out with this. So as a bit of background and probably a little recap, persistent cold air pools, or PCAPs, can cause high particulate matter concentrations during wintertime along the Wasatch Front, oftentimes leading to violations of the federal air quality standards. The high PM concentrations are largely due to buildup of ammonium nitrate, which is formed secondarily from emissions of NOx and ammonia, as well as the buildup of carbon-based species, which are largely from smoke emissions. So for regulatory and planning purposes, UDAC applies a photochemical model to assess PM 2.5 and to project PM to future levels. But that model underpredicts ammonium nitrate due to a lack of ammonia entering the system. So UDAC applied a blanket ammonia emissions increase to help alleviate the underpredictions. But this emissions increase actually introduces a major model uncertainty that could affect accuracy of projecting PM. So our work here focused on investigating causes for the modeled ammonia shortfall by looking more closely at the model response to chemical and physical processes and investigating potential underestimated or missing sources of ammonia emissions. As a part of our study, we reviewed emission inventories and compared them to measured ammonia concentration patterns that were retrieved from the WAFCO study. We also investigated modeling uncertainties and deficiencies, particularly with respect to ammonium nitrate formation. And we also reviewed scientific literature related to modeled ammonia emissions from vehicles. And finally, based on our investigations, we updated the model and reevaluated base year and attainment year modeling results. So for their SIP modeling, UDAC used CAMEX to simulate PM 2.5 during a 10-day PCAP event in January 2011 and to project PM 2.5 to the 2019 attainment year. And without going into too much detail here, CAMEX requires inputs of meteorology and emissions. The meteorology was prepared by University of Utah using WRF, and UDAC prepared emissions inputs and projected those to future years. The modeling domain is shown here. I can't use my cursor, but the purple outline shows a large regional domain encompassing all of Utah and parts of adjacent states, and this domain has grid cells spaced at 4 kilometers apart. And within that, we have a higher resolution domain with grid cells spaced at 1.33 kilometers that encompasses the region along the Wasatch Front. So let's dive into the results of the UDAC base year modeling. Here we have 2 bar charts showing 24-hour PM 2.5 concentrations at 2 monitors on January 7th, which is the day with the highest measured concentration during this episode. At Hawthorne monitor, this bar chart on the left, Hawthorne's located just southeast of Salt Lake City. Observed PM 2.5 and components are shown in the bar on the left and are compared to modeled PM 2.5 and components on the right. Here we see an underprediction in the total modeled PM 2.5. And if we look at the individual components, the underprediction is mostly attributable to underestimates in nitrate, some sulfate, and ammonium. I'll also point out that chloride, the blue bar on top, although it has a small contribution to the total, is also underpredicted by the model. And similarly for the Linden monitor, located just north of Provo, the total PM is also underpredicted, mostly due to a lack of ammonium. And so we began to dig into the physical emissions and chemical processes that might affect ammonium concentrations. Ultimately here, we wanted to try to improve model performance without having to include that blanket ammonia emissions that we discussed earlier. And so not mentioned here, as a first step, we removed that blanket ammonia emissions from the modeled inventory. And any test here shown in blue font means we retained the modification for the revised model. So the first test was to modify the vertical mixing in the model. We reduced the amount of vertical mixing to a value consistent with similar modeling exercises, and this led to improved simulated PM and gas concentrations. It also narrowed the gap in the ammonia shortfall, so we retained this modification. Next, we looked at bidirectional ammonia surface exchange to test whether the re-emission of already deposited ammonia could be a source of the ammonium shortfall. In essence, the model removes ammonia from the atmosphere via deposition to the surface, and processes were added in CAMX to allow for that ammonia to be re-emitted. So we turned on this process, but it turns out that the snow cover actually squelches the re-emissions of the deposited ammonia. In fact, the snow cover even enhances ammonia removal during the daytime when the snow starts to melt. Next, we explored potential shortfalls in the emission inventory. And so we did a literature review and found scientific literature that supports a roughly 2 times increase in the ammonia emissions from gasoline vehicles. We also found literature supporting a 40% increase in the ammonia emissions due to cold weather startups. So we scaled up the on-road mobile inventory based on this research, and model performance improved as well. In addition to investigating the ammonia emissions, we explored whether the remaining NOx under prediction affects PM2.5. To test this, we simply increased the NOx emissions by 20%, which actually resulted in lower ammonium nitrate concentrations. In other words, the system is highly nonlinear, and the lack of NOx emissions is likely not the source of the ammonium nitrate under prediction. The first chemical process we looked at, we looked into the inorganic chemistry in the model, and we used an alternative PM chemistry mechanism to test whether this model has any impact on PM, and found no significant impact. So it's likely that this model is not a source of the ammonium shortfall. Next, we looked at halogen chemistry, and you'll recall that the model underpredicted particulate chloride. But halogens can also enhance oxidation, and as a result lead to increases in other secondary PM components. So we artificially increased the concentration of chlorides in the model. And although this did help increase the particulate chloride, it resulted in negligible effects in the ammonium nitrate and total PM. We also increased the snow albedo to levels observed in field campaigns. The idea with this is that increased albedo, or how much light is reflected off the snow, would result in higher photolysis rates and enhanced formation of secondary PM. It turns out the increase had small effects on PM, but we kept this change in the model since it more accurately reflected observations. And finally, we looked at cloud chemistry and whether cloud over predictions impact PM. So we removed clouds completely from the model as a bounding test case and still found little photolysis sensitivity. Not only that, but fewer clouds led to decreased sulfate, which we did not want. So we incorporated these modifications into a revised model. And this bar chart on the far left is the same as we looked at before, showing monitored and modeled PM2.5 on January 7th at Hawthorne. And just to the right, so the second bar chart to the right, is the same chart but with the revised modeling results. Most notably, the revised model agrees more closely with observed total PM2.5. This is especially true for inorganic compounds, so the nitrate, sulfate, and ammonia. If we look at Linden, we also see improved agreement with total PM and some increases in inorganic compounds. We do, though, still see some relatively large errors, but mostly for species that have relatively small contribution to the total PM2.5. As a final step, we use this revised model to project PM2.5 to 2017 and 2019 using UDAC's projected inventory. The table here shows each monitor along the Wasatch Front with the base year design values and the future year design values based on UDAC's model and our revised model. So the two columns on the right. And you can see that the future year design value didn't change all that much between UDAC and our revised model. And also all sites continue to attain the federal standard at 35 micrograms per cubic meter. Based on our investigation, we identified and revised some key processes in the model to improve model performance and to remove the blanket ammonia emissions from the model inventory. We found that the model responded well to increased ammonia emissions from gasoline vehicles, and that scale-up was supported by scientific literature. For comparison, UDAC's ammonia injection added 65% to the Salt Lake County emissions from an unspecified source to match recent field measurements, while the ammonia scale-up in this investigation added less emissions, 40%, and from a known deficiency and an emission source. With that emissions increase and changes to the chemical and physical processes in the model, we improved modeled ammonium nitrate performance and total PM2.5, particularly in urban areas. We found that based on USU's WAFCO study, ammonia was simulated well, and also sulfate compared well to observations. However, consistent with other modeling in the Western US, nitrate particles are still under-predicted. We also found that carbon remained over-predicted. Carbon emissions in the region are largely from wood smoke, and how these emissions are split into detailed organic, inorganic, and elemental components prior to being input into the model may need some adjustment. Also, the model continued to underpredict PM2.5 at rural sites. These are sites where agricultural ammonia sources are important, but possibly underrepresented or even missing from the model. And we just mentioned in the previous slide that the projected PM2.5 design values using the updated model were similar to UDAC projections. The revised modeling also tells us that the basin is in a NOx disbenefit condition during these events, because the air has lots of NOx compared to oxidants. In other words, NOx emissions reductions can actually raise oxidant levels, and as a result, raise secondary PM formation. Because the system is highly nonlinear, this has implications for accurately projecting PM2.5 based on anticipated changes in emissions. Finally, the modeling shows that the basin is close to a balance between ammonia limited and nitrate limited conditions as it relates to ammonium nitrate formation. In this case, the model is in agreement with recent field studies, but there are still some important model uncertainties and biases that could affect how PM2.5 responds to changes in emissions. So it's still important to try to resolve these remaining uncertainties. Based on these conclusions, we've provided some recommendations for future modeling. First, we recommend modeling a more recent PM2.5 episode, and this new model should also incorporate the key updates we have identified in this project. We also didn't really discuss meteorology in much detail here, but these MET simulations are obviously very important in predicting PM concentrations during a PCAP. So we recommend investigations into potential improvements in these MET simulations. And regarding the emission inventory and how the inventory is spatially allocated in the model, Based on our review of the inventory and findings from the WAFICO study, we recommend improvements to emissions from livestock and landfill sources in particular. We also recommend further investigation into the NOx and chloride underpredictions, the chemical speciation for wood smoke emissions, the role of snow in surface atmosphere ammonia exchange, and finally, the impacts of all these updates on PM 2.5 responses to future or alternative emission scenarios.